My dear viewers, welcome to once again the Future Not Bank Refraction Part 2. In Refraction 1, you got explanation regarding the main concepts. But in the Refraction 2, you are going to pair the mainly the ray diagrams and the how to draw the ray diagrams and having certain rules also. So complete ray diagrams and rules and some important questions also you are learning in the part 2. I think hope so you will be the refraction will be very smoothly going in your examinations. Now I am going to explain first of all the rules how to go for the ray diagrams by using the convex lens, how to go for the concave lens, and what is the differentiation in the convex lens means you can see how to this is the if the arrow marks are downwards on the both the sides arrow marks are there means that is a convex lens. Here the V-shaped inverted V shape is there means that is a concave lens. This is the differentiation between these two. Now first rule, this is the principal axis. Because of the lens on the either side it is having the center of curvature and it is having two radius of curvatures, and that means two radii. Here one is C1, another one is C2, and F1 and F2, and two focal lengths and two radii curvatures we are having. Now this is the principal axis which is passing through the optic center of the lens, and first rule is whenever the incident ray is passing parallel to the principal axis and after refraction, see the ray entered into the lens, convex lens, the ray is refracting, bending down, exactly it is passing through the focus. Exactly it is passing through the focus. Once again, the incident ray which is going completely parallel to the principal axis after refraction, that means bending of the light, the refracted ray is passing through the focal point here. That is rule 1. And comes to the point of rule 2. Here you will make it confused. Here the incident ray is following the principal axis. Whenever the incident ray is exactly following the principal axis and without any hesitation, the refracted ray will go undeviatedly in the along with the principal axis. So there is a no deviation, no refraction in this case if the incident ray is passing through the principal axis in the rule number 2. And rule number 3, the incident ray is passing through the optic center. If it is passing through the optic center, that ray also undeviatedly is going forward. Here two cases you can see. If the incident ray is passing through the principal axis going undeviatedly, and if the incident ray is passing through the optic center also going undeviatedly. The rule number 1 is the incident ray is parallel to the principal axis, the refracted ray is going through the focal point. And the fourth one, the incident ray is passing through the focal point and then meeting the lens, and the refracted ray is going parallel. And what vice versa situation you can see. Vice versa situation means the fourth one and the first one you can see. The fourth one is incident ray is going through the focal point and the refracted ray is a parallel to the principal axis. In the first one, the incident ray is parallel to the principal axis, the refracted ray is a focal point. That means here beginning is focal point, ending as a parallel. Here beginning is parallel, ending as a through the focal point. That is a similarity you are finding in the convex lens. So these are the 4 rules. Glance clearly. Once again, roughly I will go through. If its incident is parallel, refracted ray moves through the focal point. If incident ray is through the principal axis, go undeviatedly in the rule 2. Even though in the incident ray is passing through the optic center or midpoint of the lens, undeviated is going. 2 occasions undeviated is going here. Whenever it is passing through the principal axis and here passing to the optic center. And the fourth case, if the incident ray is passing to the focal point, The refracted ray is going to the parallel. This is a vice versa case in this case. And comes to the point of here, concave lens. First rule, if the incident ray is a parallel, like in this case also, but the refracted ray is going diverging away, and what is happening? If the refracted ray seems to be meeting the focal point, it looks like, but it exactly is not meeting. That purpose we kept the dotted picture here. The incident ray is parallel, the refracted ray is going away, not parallel, not even passing through the focus, also going away, and but the reflected ray imaginarily is going to be looking like it is going to be from the focal point. The next one, rule 2. If the incident ray in the concave lens is going to the principal axis undividedly, same as it is in this concave lens, here also the incident ray is passing through the optic center undividedly. Now, here the rule number 4, if the incident ray is pointing towards the focal point, seems to be pointing towards the focal length. After refraction, the refracted ray is going to be parallel to the principal axis. Here, same vice versa case as we seen in the convex lens. In the convex lens, first rule, incident ray is parallel. Here, refracted ray is parallel. In the fourth case, refracted ray is parallel. In the first case, first rule is incident ray is parallel. Now, in the first case, the refracted ray seems to be meeting the focal point. Here, the incident ray meeting to the focal point. Seems to be meeting. Seems to be meeting means it is imaginary, not a real sidence. So these are the rules which you have to follow. Once again, I repeat these concave rules. Incident ray is parallel, the refracted ray seems to be going through the focal point. Rule 2, if the incident rays through the principal axis will go undeviatedly along with the principal axis. If the incident ray is passing through the focal point, optic center, it is going undeviatedly. If the incident ray seems to be meeting the focal point, but after the refraction going parallel to the principal axis. These are the 4 rules from the convex lens and 4 rules for the concave lens. Now we'll go for the ray diagrams. A 1 minute, a short break. Once again, after the little break, we'll come back to the very important things over here. Ray diagrams. The ray diagrams are, I think, you can see these are the very key role it's playing. One is, and in the ray diagrams means you can see in the ray diagrams what are you going to learn? Position of the object, position of the image, nature of the image. In the nature of the image, we have to find out whether it is real or virtual image, inverted or erect, diminished or enlarged. These three properties we call as nature of the image. So totally 5 points we are learning from each one. Now we can see in the first case, this is the lens and this is the convex lens here. In this convex lens, principal axis we can see there. Whenever we keep the object, beyond C, and after refraction, the image is forming between F and C. Now, what you will say? Position of the object is beyond C. If the position of the object is beyond C and the position of the image between F and C always. And now we will going to measure the distance. The optic center to object is greater distance. The optic center to image is a shorter distance. Because of the shorter distance point of view, the image is going to be diminished. Once again I will repeat, the distance from the optic center to image is lesser when compared to that of the optic center to object. And then first is position of the object is beyond C. Position of the image is between F and C. And the nature of the image means whether you have to say real or virtual. It is real image. How can we say? What is the evidence to say the real image means? Because object and the image on the either side of the lens. If the object and the image on the either side of the lens, then it is going to be called as a real image. So it is a real image and inverted image and diminished image. Real, inverted, diminished. Which case you will find this one? If the object is placed beyond the C, image is forming between F and C. So why the diminished is forming means I already told that one. The distance when we are measuring from the optic center to image is going to be shorter. The optic center to the object is longer. Which is having long distance always greater in size. Which is having a shorter distance always smaller in size. So the diminished image we are getting here. This is the case number 1. Now second position where I am going to keep the object. Second position is I am keeping the object exactly on the center of curvature C. Exactly on the center of curvature C. And here the image also is forming on center of curvature. This is the in the mirrors rule also you will find the same. In the mirrors rule also you will find the same. If the object is on the center of curvature, position of the object is on center of curvature, position of the image also on center of curvature. I will repeat. Position of the object is on center of curvature, position of the image also on center of curvature. So the distance for both from the optic center, both for image and object is same. Whatever the distance is there from the optic center to object, similar distance you are having from the optic center to the image. And due to this concept, the size of the object and the size of the image are equal. Either it is not enlarged or it is not diminished. It is same size of the image. And you may get in the examination one question. When do we get the same size of the image? Where do I keep the object means that time you have to say, you have to give the answer. If you are keeping the object on C, we will get the image on C, same size of image you'll get. So that is the range you have to find out. And comes to the point of the ray diagram number 3. The object is keeping between center of curvature and focal point, in between, and the image is forming beyond C. The image is forming beyond C. Now we will go for the measuring of the distance. A distance from the optic center to object is smaller, and the distance from the optic center to image is greater. And here image is the having the greater distance and object is having the lesser distance. Due to this lesser distance point of view, object is a smaller, image is greater. Image is greater because from distance from the optic center to image is very high. So what kind of image we are getting means enlarged image. Automatically we can say enlarged image. In the problems point of view, whenever we are getting the certain problems, in the problems I will take one complete episode regarding the problems of the reflection of the light in the first lesson and the refraction of the light in the fourth lesson. Problems at a stretch, in a single video I will go through for all the problems. But before I go into say, in the problems, if you got object is in the distance is 20 centimeters, in the answer is asking to find out the image distance. Image distance you got the 30 centimeters means automatically you can say the image is enlarged. The image is enlarged. So image is enlarged. When you get the enlarged image, when the object is between F and C. This is the technically how to go through. When the object is F and C, when the object is F and C, the image is going to be the enlarged. When the object is on C, image also same side. If you want the diminished image, when you get the diminished image, if the object is beyond C. This is the technique. If the object you place the beyond C, automatically the inverted image, diminished image you are going to get. If the object is on C, same size you will get. If the object is between F and C, the enlarged image you will get. Now, next case, fourth case, if the object is your placing on the focal point, object is placing on the focal point, you will get real image, there is no doubt about it, but you won't find the image. You won't find the placement of the image. It will be infinity. If that object is on focal point, image is on infinity. But one ray diagram we are forgetting here. What is that means? Object is at infinity. Object is on F focal point. Object is on focal point. Image is at infinity. Once again I'll repeat. Object is on focal point. Image is at infinity. I will repeat. Object is at focal point. Image is at infinity. If the object is at infinity, image is on focal point. If object is at infinity, image is on focal point, that image will be point size image. That is the reason we are not going to draw the ray diagram for that image. What image? If the object is placed at infinity, image 100% a point size image we will get on the F. And in the exams one question you will get. What kind of question? When do you will get the point size image? When you are keeping the object at infinity, or almost you are getting the point size image. And when you will get the infinity image, when you are keeping the object at F. And comes the point of the ray diagram number 5. If you are keeping the object between P and F, that means optic center and focal point. And now object is too close. Object is very close to the optic center. And that occasion, almost all you can see, whenever object is very close, image almost all it is very far. Object is very close means think that one vice versa, image is very far. So image is forming on the same side of the object. Whenever the image is forming on the same side of the object in the lenses, that is going to be the virtual image. Here, one interesting 2 marks question you will get in final exam says, what is that? When do we will get virtual image in lenses? You have to say if the object is keeping between P and F. Same question, when do we get the virtual image in case of the mirrors? Same answer you are going to get. Object has to keep between P and F. But here virtual image means the object and image both on the same side. That is going to be the virtual image. In the mirrors, object is one side and image is the other side. That is the virtual image in the case of the mirrors. So these are the very important 5 ray diagrams. And very simply I will say enlarged image, diminished image getting if the object is beyond C. Same size image is getting when object is on C. Enlarged image you are getting when you are keeping the object between F and C. Infinity image you are getting if you are keeping on F. And enlarged virtual image you are getting when you are keeping the between P and F. And one fact you have to know that all the real images are inverted. All the virtual images are erect. This is the point, key point you have to write down regarding the ray diagrams. Okay. Now we will go for the next few questions after. Okay, right? Now, after this ray diagrams, some few concepts I am explaining here. And the first one means, first question is see, is the focal length of biconvex lens? Is the focal length of biconvex lens? Biconvex lens is positive or negative. How can you? That means what is the technique? What is the technique you will use to find the focal length of a biconvex lens is positive or negative? Here we are discussing about how to find, yes, the focal length is negative, yes, the focal length is positive. This kind of complete clarification we are going to see the answer. Now what is actually, we have to go for here. To find out this one formula I have to go through. What is that formula? Lens makers formula. 1 by F is equals to N2 minus N1 minus 1 into 1 by R1 minus 1 by R2. Here, try to go for the terminology. N2 means refractive index of the medium 2. N2 means refractive index of the medium 2. Suppose lens means automatically one is air, that is a rarer medium, another one is lens, that is a denser medium. So the denser medium refractive index is N2. Refractive index of denser medium is N2. Refractive index of the rarer medium air is N1. So N2 minus N1 minus 1 is equals to R1 minus R2. You know already, just now I told you, lens is having two radii. Radius of curvatures are 2. F1 and R1 and R2. So, and why you are taking the negative means, if the the radius of curvature measuring in front of the lens, we are taken as positive. The radius of measuring the back of the lens is taken as negative. I will repeat. The radius of curvature is going to be positive if the measuring the radius of curvature in front of the lens, and we are measuring the radius of curvature back of the lens is going to be the negative. So R1 is positive, R2 is negative. Now here you can see in this calculation, when N2 is greater than N1, that means refractive index of N2 is greater than N1. Refractive index of N2 is greater than N1. That means refractive index of the lens is greater than the refractive index of A. That occasion, focal length of the focal length should be taken as negative. I told we have to learn the technique. What is the technique means? We are measuring the refractive index of the air, that is N1, refractive index of the lens, that is N2. In this case, the refractive index of the lens is greater than the refractive index of the air. That occasion, focal length is taken as negative. Focal length is given in the problem's calculation point of 15, you think. Minus 15 you have to take. You have to consider in the calculation minus 15. If N2 is greater than N1. Now, this one is N2 is less than N1. N2 is less than N1, we have to take negative. If N2 is greater than N1, should take taken as positive. I will repeat that answer once again. The refractive index of the glass is less than air. The refractive index of the glass less than the refractive index of the air. That occasion, focal length should be taken as negative. If the refractive index of the glass is greater than the refractive index of the air, focal length is taken as positive. This is the way we are going to find out that technically the focal length is whether it's negative or positive. Now I will repeat that one. That means the focal length depends upon the surrounding medium. So it is whether it is air or glass, air or water. Two formulae I am giving here. Note down these two formulae for the sums calculation point of view. How to find out the curved surface. Curved surface formula. Here, curved surface formula means N2 minus V N1 minus U is equals to N2 minus 1 N1 by R. This is the formula we'll use to calculate the curved surface. N2 means refractive index of the medium 2 and image distance, refractive index of the medium 1 and object distance, which is equals to N2 minus N1 by radius of curvature. This is called curved surface formula. Now we'll go for plane surface formula. Plane surface. Plane surface formula is N2 by V is equals to N1 by U. And that means refractive index of the medium 2 by image distance equal to refractive index of the medium 1 by object distance. This is the two formulae we are going to face. Now, next important concept is, can virtual image be photographed? Can virtual image be photographed? Photographed by camera. That means virtual image ने camera तो photo తీయొచ్చా? Is it possible to take a photo with the help of the camera, the virtual image? Then answer is going to be yes. But what will be the reason? Here is the reason, because we can focus on the image and that forms on the same side of the using the lens. So that means in the lenses the object and image, virtual image. When we will get virtual image? When the object and the image on the same side, that time we can call virtual image in the lenses. In the lenses we will call virtual image. In which position? The position of the object and the position of the image going to be on the same side, we can call it the virtual image. Whenever you are taking the concentrating on the object with the camera, automatically the virtual image also going to be get photographed. So it is possible. And but if it is a virtual image on the other side of the lens, it is not going to be possible. So then the question, you can get the answer, can virtual image be photographed by camera? And yes, it is going to be photographed. Reason is both are on same side. The image as well as object on the same side. And now here very interesting topic I am going to explain now. What is that means? Radius of curvature, focal length. What is the relation between these two? Means from the mirrors onwards you are learning one concept. Radius of curvature is nothing but double of the focal length. If the focal length is 5 centimeters, radius of curvature is 10 centimeters. If the focal length is 15 centimeters, radius of curvature is 30 centimeters. And radius of curvature, that means focal length is equals to half of the radius of curvature. This is the relation we are getting between radius of curvature and focal length. But here, now I am giving one derivation. In the lens, also same criteria you are going to face. What criteria? Radius of curvature is equals to double of the focal length. But in one case, both radius of curvature and focal length are equal. Which condition both radius of curvature, focal length is equal? Actually, radius of curvature means 100%, it is a double of the focal length. Here, when the lens is having refractive index of 1.5, the lens is having refractive index of 1.5, that occasion, both radius of curvature and focal length are going to be get equal. With mathematically I will show you here. By using the lens maker's formula, 1 by f is equals to n minus 1. N here represents refractive index, and here 1 by r1 minus 1 by r2. Here then because of the convex lens, per convex lens here going to be positive, R2 is going to be negative. R1 is going to be the positive, R2 is going to be the negative. And the refractive index is 1.5. So here that means R1 is equals to R2. Both are equal. And so In that formula, 1 by f is equals to, in the refractive index is 1.5, 1.5 minus 1 is equals to 1 by r plus 1 by r. Reason is here, first is positive radius of curvature, second one is negative radius of curvature, but in the formula negative into negative will get the positive. So that purpose and the measurement of both radius of curvature is the same. So when we are taking this one as a ratio point of view, here is 1.5 minus 1.5 minus 1 means we will get the answer is 0.5. And here after the LCM we are going to get as a 2r. You are going to get a 2r. Now we can see when you are taking the LCM of 1 by r plus 1 by r, we are getting the 2r. Now we can write 0.5 as 1 by 2. 0.5 as 1 by 2 into 2 by r. Now 2 going to get cancelled. We got 1 by f is equals to 1 by r. Therefore, f is equals to r. That means focal length is equals to radius of curvature. That means if the radius of curvature, both radius of curvature lengths are equal, they are opposite each other. One is a positive, another one is negative. Refractive index is 1.5. That occasion, focal length as well as radius of curvature going to be equal. So these are the concepts so far I explained. In the next class regarding the what you call reflection of the light in the first lesson and refraction of the light in the fourth lesson, you are having so many numericals and many people are struggling for the numericals. And to complete that episode, I will go with the numericals only. Both the lessons numericals you are going to see. Okay, thank you for watching.